Diffusion. Open, efficient image generation via latent diffusion. Agenda: Diffusion model efficiency. Stable diffusion history. Why stable diffusion? Latent diffusion lifecycle. Getting started. Basic workflow: encoding and denoising. Diffusion model efficiency. Diffusion models generate high quality images, but running the entire denoising process directly on full resolution pixels is extremely computationally expensive. If every diffusion step has to process a full-size image pixel by pixel, generating even one image can require enormous amounts of compute. Almost every practical image generation system has to find a way to reduce that computational cost without sacrificing quality. Any tool meant to run on ordinary consumer hardware benefits from doing less work per step while still producing sharp results. Requiring cluster scale GPUs just to generate a single image doesn't scale to individual creators and developers. Pixel space and latent space diffusion. Pixel space diffusion runs the entire noising and denoising process directly on full resolution images, which is accurate but computationally heavy. Stable diffusion instead compresses an image into a smaller latent representation first and runs the diffusion process there instead. Pixel space, full resolution images, heavy compute per step, needs cluster scale GPUs. Latent space, stable diffusion, compressed representation, runs on consumer graphical processing units GPUs. Problems with pixel space diffusion. Single point of cost. Denoising a full resolution image at every step demands far more compute than necessary. Cluster scale GPUs become a practical requirement, putting the technology out of reach for individual developers. Slower generation times make iterating on prompts and settings frustrating. Memory requirements scale directly with image resolution, limiting what's practical to generate. Running models locally rather than through an expensive cloud service becomes difficult or impossible. Misses out on the accessibility that comes from a technique efficient enough to run on ordinary consumer hardware. The stable diffusion system. An image is compressed into a smaller latent representation using a variational autoencoder (VAE) before any diffusion happens. Then the original image. A U-Net model performs the actual noising and denoising steps within that compact latent space, guided by a text encoder's understanding of the prompt. Once denoising is complete, the variational autoencoder (VAE's) decoder expands the latent representation back into a full detailed image. Other well-known image generation tools: Midjourney, DALL-E, Adobe Firefly. Stable diffusion advantages. Runs on consumer GPUs. Unlike earlier diffusion models that needed cluster-scale hardware. Open, publicly downloadable weights let anyone run, inspect, or fine-tune the model locally. Latent space diffusion dramatically reduces compute and memory requirements without sacrificing quality. A large open-source ecosystem has grown up around it, including fine-tuning techniques and add-on tools. Full local control means no per image cost and no dependence on a cloud service staying available. Multiple released versions have steadily improved image quality, prompt accuracy, and resolution. Everything is compressed before it's diffused. One huge benefit of this design is that in stable diffusion, almost every step of the actual diffusion process happens on a compressed latent representation, not the full image. The VAE encoder shrinks an image into a much smaller latent space before any noise is added or removed. Because the latent space is so much smaller than the full pixel grid, every diffusion step costs a fraction of what pixel space diffusion would require. Only at the very end does the VAE decoder expand the finished latent back into a full resolution image. This compress diffuse decompress pattern is the core technical idea that made efficient, locally runnable image generation possible. Encoding and denoising. Encoding, compressing an image into a smaller latent representation. Denoising, predicting and removing noise within that latent space. A simplified latent encoding step. An image is compressed into a much smaller latent representation before diffusion begins. A simplified denoising loop. Denoising happens entirely within the compact latent space, guided by the prompt. History. Built on latent diffusion models, research published by Robin Rumbach, Andrea Blackman, and colleagues at the CompWiz group at LMU Munich in 2021 and 2022 developed into stable diffusion through a collaboration between CompWiz, Runaway, and Stability AI, with support from Leon (LAION) and Eleuther AI. Publicly released on August 22, 2022, with openly downloadable weights, unlike closed contemporaries such as DAL-E 2. Training relied on a subset of the Leon 5B image text dataset (LAION 5B) image text dataset with Stability AI covering the substantial compute cost. Later versions, including SDXL and Stable Diffusion 3, continued to improve quality and introduced new architectural refinements. Why Stable Diffusion matters? Efficient. Latent space diffusion made high-quality image generation practical on consumer CPUs. Open, publicly available weights let anyone run, study, or fine-tune the model. Accessible, removed the requirement for cluster-scale hardware or an expensive cloud service. Influential, established latent diffusion as a dominant approach across the field. Community-driven, sparked a large ecosystem of open-source tools and fine-tuned models. Transparent, an open model that can be inspected unlike closed API-only alternatives. The variational autoencoder, a variational autoencoder, learns to compress images into a smaller latent space and reconstruct them back again. The encoder and decoder are trained together so that compression loses as little visual detail as possible. A typical downsampling factor shrinks an image dramatically while preserving what the diffusion process needs to work with. Never assume the latent representation looks anything like the final image. It's a compact, abstract encoding, not a low-resolution thumbnail. Encode, compress to latent, add noise, diffuse, remove noise per prompt, denoise, expand to full image, decode. An image or noise is encoded into latent space, diffused, that is, a noise is added to it, and denoised there, guided by the prompt, then decoded back into a full resolution image. Getting started with stable diffusion. This leads us to the three steps that get your first image generated. Choose an interface. Pick a local tool or hosted service to run the model. Get a checkpoint. Obtain a model checkpoint suited to your needs. Write a prompt. Describe the image you want to create. Basic workflow. Prompting, fine-tuning, and rendering. Some call prompt, fine-tune, and render stable diffusion's everyday loop. Detailed prompts, along with negative prompts, help steer results toward what you actually want. Community fine-tuning techniques let a base checkpoint be adopted to a specific style or subject. Additional tools like Control Net add precise control over composition and pose. Rendering speed and quality can be tuned by adjusting the number of denoising steps. Supports many workflows: illustration, concept art, product mockups, and creative experimentation. Works the same whether run locally on your own GPU or through a hosted service. Any questions? Thank you.